So this is part one. This video is just meant to give you an introduction into implicit differentiation, is what section 2.5 covers. So in this video, I'll just go over the concept, and then the following videos would be over examples. So we've dealt with a function like this, where it's y equals x squared minus 3. Y is written explicitly as a function of x. So sometimes instead of y, we could write it as f of x equals x squared minus 3. They just use the letter y for convenience sake. So we could have wrote it as f of x equal to x squared minus 3. But most of the time, or not most of the time, but sometimes we just use the letter y instead of the function notation. But the point is that it's y equals, and then on the right side is an expression involving the variable x. That means y is written explicitly as a function of x. And to find the derivative, we did the notation I was using was y prime, and then equals d dx, and then in brackets is the expression which we're taking the derivative of. Now, the derivative is an operator, so it's saying, even though it looks like it's like a fraction, but then this is notation. It says take the derivative with respect to x. So what variable is in the denominator is the variable in which you're taking the derivative with respect to. So x squared minus 3, the derivative of x squared is 2 times x because of the power rule. And then derivative of minus 3 is 0 because that's a constant. So y prime is equal to 2x. That was what the answer we would go with as its derivative. And note that I'm using y prime instead of using the notation that might be used in the textbook or somewhere else. It's dy dx. So you could write it as dy dx equal to 2x instead of using y prime. And you'll see in a second why I'm bringing back this notation. So all of this was discussed in previous videos about the notation using y prime versus dy dx. And again, it's not saying dy divided by dx, it's an operator. It's saying take the derivative of the function y with respect to x is what that dy over dx notation means. And its derivative is 2x. All right, so that's nothing new. But the point is that this is a function y written explicitly as a function of x. And we've done all of our examples up to this point, dealt with finding derivative of such type of functions. Now, what happens when you have x squared plus y squared equal to 9? So now I have this y squared. And I also have it involving, so x squared plus y squared are both on one side. And then I have, the main point is that I have a y squared versus here's y. And so we can't say it's in y's written explicitly as a function of x. This is not explicit form. This is called implicit form. And so we're going to use what's called implicit differentiation to find the derivative of such type of equation. Now, from algebra class or trigonometry class, this x squared plus y squared equal to 9, that is the equation for a circle and with radius 3. Right? The circle equation is x squared plus y squared equal to r squared if the center of the circle is 0, 0, and then the radius is r. So this is just added information, sort of an aside, just to make sense of what this equation is. It's the equation of a circle centered at the origin 0, 0 with a radius of 3, because r squared is 9. All right, so for implicit differentiation, we will still use the dy dx operator, but in a quote special way. You'll see in a second what I mean by special way. Now this whole time when we're doing the derivative of some expression like this, we're using y is assumed to be defined implicitly as a differentiable function of x. All right, so yeah, this is not explicit form. It's called, and we're going to use implicit differentiation. The dy dx is an operator, and we're the derivative, and we're using it in a special way. And this whole time, we will be assuming the variable y is assumed to be defined implicitly as a differentiable function of x. So that's important for how you use the notation dy dx. All right, so before I work out that problem, here are the guidelines for implicit differentiation, and these are just also written in the textbook. But essentially the first step you do is you differentiate both sides with respect to x, right? Because that's what the dx part means, taking the derivative with respect to x. You're going to collect all terms involving dy dx, and I put in parentheses y prime. So I'll show the problem worked out using the dy dx notation, and then from here on out, I will be using y prime instead. So you're going to collect all terms involving dy dx on the left side, and then move all the other terms to the right side. We're going to factor dy dx or y prime out of the left side, and then you're going to solve for dy dx or y prime. But these are the guidelines. So I'm going to make sense of these guidelines working out the problem. All right, so x squared plus y squared equal to 9. So we're going to differentiate that. So the first step is differentiate both sides with respect to x. So that's why I have dy or d dx, taking the derivative with respect to x, and then bracket the whole left side, and then d dx, and then in brackets the right side. Now the way you take the derivative, so you use the power rule for these variables. So like derivative of x squared, you're just going to use normal power rule. So we're going to use the normal derivative rules. Nothing's different there. And so first thing is I separate it, so I'm taking the derivative of each term, x squared and y squared. Now the derivative of 9, that's 0 because that's a constant. All right, this is where we get into something different. So taking the derivative of x squared, that's 2x. That's normal derivative rules. Now for y squared, this is where it gets a little different. We still take the derivative of y squared like we would if it was x squared. So we drop down the exponent using the power rule, and it'd be 2y to the 2 minus 1, which is 2y, just like this was 2x. The only added difference is now I attach this term, or this operator called dy dx. And I do that for any time I take the derivative of some expression, and that expression involves the variable y. I'm going to always attach this when taking the derivative of some expression that has variable y. And again, we're just using implicit differentiation for this chapter or section. All right, and that's what I wrote in yellow or gold. So I have 2x plus 2y, and then, 2x plus 2y, and then this dy dx part attached to the 2y, and then equals 0. All right, that's taking the derivative with respect to x. Now I'm going to collect all the terms for dy dx on the left and move all other terms to the right side. Well, there's only one term with dy dx, it's the 2y part. So the other term, 2x, is I bring it to the right side, so I subtracted 2x from both sides. Then I have 2y, then dy dx equal to negative 2x. There's really no factoring out because we only have one term. So all I got to do is solve for dy dx. And that means just get it by itself. Well, to get dy dx by itself, I have to divide by 2y. That's what I did. I divided by 2y from both sides, and then you have dy dx equal to negative 2x divided by 2y. And then I just divided the 2's out to get negative x over y. And then this is going to be my answer. And again, the dy dx is going to be by itself on the left side, and then you're going to have some expression involving x and y on the right side. And that's how you do implicit differentiation. And instead of using dy dx all the time, I'm going to use the notation y prime. So I'll recap the same problem, just using the new notation. So the first step, take derivative with respect to x to both sides. All right, so that's the first thing I do. Then and in that process, I take the derivative of x squared, derivative of y squared. So I just put the operator to each term. Derivative of 9 is 0 because that's a constant. Now derivative of x squared, that turns into 2x because of the power rule. Derivative of y squared turns into 2y, but then I attach y prime. So instead of dy dx, I use y prime. It's just less, I don't know, stuff to write. But the idea is still the same. I want to get the y prime by itself. So the first thing, I subtract 2x from both sides. That was what I did before. And then I divided by 2y. So it'll be y prime equal to negative x divided by y. Same thing as just writing it as dy dx equal to negative x divided by y. All right, and the main important thing here is that I attach this dy dx to any variable or any term involving the variable y. And that's because of the chain rule. Okay, so that's for this video, is just explaining how you use implicit differentiation, went over the guidelines, did an example. And for the next videos, I will be using this notation, or it's y prime versus dy dx, even though they mean the same thing.